This is a clean glean on acceleration. In this video, we want to better understand this picture. We're going to start with a definition. We have r vec. We want it to be twice differentiable. The first derivative we'll set to be the velocity vector, v vec of t. The second derivative, that's a derivative on velocity, is the acceleration vector, a vec of t. And that if we go back to velocity, that's a vector, and we take its magnitude, that we can denote as v of t, that is the speed. All right, so note that you want to be careful with your notation. When you write velocity, you want to make sure that you're indicating it's a vector, as we have v vec of t for velocity and v of t for speed. Velocity and speed. That speed is the magnitude of velocity, and that velocity taken to be a derivative on the position vector is the same thing as, when looking at speed, as the norm of r prime vec. And then recalling back from a previous video on arc length, that the arc length function s of t is defined as an integral, with the integrand being the norm of a derivative on position. By the fundamental theorem of calculus, ds dt is the integrand. Nice. So if you need to go back and review arc length, click in the upper right, and then let's continue. So this may be a familiar setup if you recall rectilinear motion. And it's basically the same thing, but with, instead of a position function given by a scalar, this is position function given by a vector valued function. And then this is nice because we can use it to describe moving objects, moving particles, for example, a car. We can represent the car with a dot on the curve that it follows, the trajectory. So pick a dot. Let that correspond with parameter t being set to t naught. The vehicle, if it is not turned one direction or other, would head in the direction of velocity, here given in green. So that's v vec. And what we're going to want to come and understand is that if we take a vector parallel to velocity and scale it by an amount at, and then if we go and look at a normal direction to velocity and scale that direction by an, that the sum of these two vectors, these two orthogonal vectors, yield the acceleration vector. Okay. So that's our objective, is to come up with this equation to better understand it. Let's look at the pieces. We had velocity. Velocity is normalized, produces the unit tangent vector. We know from a previous video that orthogonal to the unit tangent is the unit normal vector. And that this equation is showing that the sum of the vectors on the right produces the vector on the left, namely acceleration. As we're breaking up acceleration into this piece and that piece, where the two pieces have nothing to do with each other, they are orthogonal, this is a vector decomposition. Now, acceleration, we're going to show, can always be decomposed in terms of a unit tangent vector and a unit normal vector. And as such, acceleration will always lie in the osculating plane, or be parallel to the osculating plane. Okay, let's be a little bit more precise here. Let's not forget about the scalar functions, that there's a scalar function on the unit tangent, there's a scalar function on the unit normal. These are then providing the tangential and normal components of acceleration. All right, and so you want to get comfortable with that notation. And if you're looking very closely, acceleration is in one type font, the lowercase a, and then the scalars components are in a different font, lowercase a. Nice. And here I've used color to indicate scalar, orange, and blue, vector. Excellent. So this is our objective for the video. And this in the book is under the components of the acceleration vector. And it's making mention of the previous section, arc length and curvature. If you need to, you can go back and you can reference that video, click in the upper right. So curvature was given by kappa. Here we're going to establish this theorem 3.7, namely showing that acceleration has this decomposition. You'll note that the normal and tangential components are taking a different form than what we saw earlier. Let's go ahead and look at why these should be the scalar components. So remember that we defined velocity as a derivative on position. Recall also that the unit tangent is a derivative on position normalized. Since a derivative on position is velocity, we can solve for velocity in this equation of the unit tangent and come up with velocity expressed as speed scaling the unit tangent. Okay, then look at the theorem that we're trying to establish, and it is a theorem for acceleration, and we know that acceleration is a derivative on velocity. So we're going to take the derivative of the velocity vector, and we're going to use that it's speed scaling the unit tangent vector. So we go ahead and we set that up. V prime vec will be d by dt on speed scaling the unit tangent. That's a product, a scalar product of the unit tangent. Therefore, we get two pieces. One piece where the derivative hits speed, and one piece where the derivative hits the unit tangent. All right, we're already looking pretty good. We have a sum of vectors to express out acceleration. And we're going to focus here on t prime vec. You'll recall from a previous video that t prime vec is orthogonal to the unit tangent vector, that the unit normal is simply t prime vec normalized. And with that simple definition, we can then solve for t prime vec as a scalar multiple of the unit normal vector, and then plug in to the equation. Represent t prime vec now as the norm of t prime vec scaling the unit normal. And look, now we have acceleration decomposed into the unit tangent and the unit normal, scalar multiples of. Nice. So we're almost done. We now look at, well, what's an expression for the norm of a derivative on the unit tangent? And we can think back to that curvature video and know that kappa, as the first alternative formula, is this quotient. And thus, the magnitude of a derivative on the unit tangent is kappa multiplying the norm of r prime vec, but the norm of r prime vec is is speed. Okay. So plugging that in, we establish our desired form. And the proof is finished. Here's the proof that here's the theorem that we just finished our proof of. All right, well, let's pause for a second here and look at what we've come upon. And recall that we were interested in these scalar components. So that v prime is the tangential component, and speed squared product with curvature is the normal component. Looks pretty complicated. And indeed, the computations are rather involved. Let's take a look. Well, we would need to find velocity, the velocity vector, r prime vec. From the velocity vector, we could then find the speed function, v of t. And note that the tangential is simply a derivative on speed, so we'd have to take that derivative. And here you note d by dt of a magnitude. Well, magnitude is a square root of some. That's rather involved, taking the derivative. That's chain rule for sure. And we would also need the unit tangent vector. Why? Because the normal component involves curvature. Well, yes, that is a lot of computation. So why in the world should we get so excited about the tangential and normal components when it's so involved? Well, we actually have simpler computations for coming up with the components of acceleration, a sub t and a sub n. And this I'm going to give to you as an assignment to verify that the tangential and normal components take these forms. And I give you 2 hints. First, that the unit tangent is in the direction of velocity, and it's velocity normalized. And then if you look at the first statement that the unit tangent is velocity normalized, okay, well, that's really establishing this equality. Then you want to reason why this should be true. And then the second one, well, we have the norm of a cross product. So what is this norm of the cross product? Remember that that's giving the area of the this is giving the area of the parallelogram determined by the 2 vectors, vvec and avec. And then remember that sine is in a triangle, right triangle, opposite over hypotenuse. So that should help you out with this piece here. And this piece over here, well, you might go back and reference this picture that we had earlier and try and spend some time in this picture. Notice that there's a theta present. Theta is between velocity vector and acceleration vector. Nice. So that assignment is a good assignment. Let's make use of those formulas, which I've given for you to verify in this example 315. Let's go ahead and copy out the position vector. Off to the left are the formulas that you're going to verify. And then taking a derivative of position, we get velocity. And then we can write out acceleration. That's a derivative on velocity. And then we can see that for the tangential component, we're going to want to take the dot product of velocity and acceleration and then divide through by the length of velocity by speed. So that's just a computation. Here, quote the formula we want to use, and then make the computation. And then once you finish with the computation, this is done for all values t that hold, so that we're getting the tangential component of acceleration as a function of t. Good. Let's bring this tangential component off to the side and then move on and look at the normal component. And the normal component is using this. Note that this is really here in the dashed red box, that's essentially the Pythagorean theorem isolating out a side of a right triangle. All right, and then highlighted in gray, that's the tangential component, so that's a sub t, quantity squared. And then looking at the acceleration vector, we want to take its norm. That's by this formula. And then it's just a straight computation to figure this out. And again, we get that the normal component of acceleration is a function depending on t. This is to come up with acceleration at any time t. Beautiful. So here's one for you to play around with. And that is a clean glean on acceleration. Thanks for watching.